Air pollution was not a conventional topic to be taught in engineering, but IIT Kanpur was ahead of time at that point. These weather models are created by more than 100 scientists in a span of 50 years.
Your work highlighted that dust is a bigger threat than the black carbon to Himalaya.
There is famous theories that temperature over Tibet drives our monsoon. For example, California state, they start to quantify wind energy can run this city for 3 hours a day. After BTech, someone would come and tell you there is a set of mathematical equations. If you can solve them numerically, you can simulate the storm happening outside your window. I was part of a project with NASA. Why they have invested so much in 30 years to build Earth observations. If you have lot of pollution in a rising parcel, it can change the microphysics of cloud. What was even more fascinating was there was a LIDAR, a ground-based LIDAR, which can sense the atmosphere up to 20 kilometers. We started to see that North India has around 2 kilometer thick layer of dust particles in the atmosphere.
Oh.
So I gave you an aha moment.
I had my aha moment. Hello all, welcome to another episode of Know Your Professor by CA IITM. I'm Ritika, final year MTech student in BTCM here at IIT Madras. Today we have Dr. Chandan Sarangi sir here. So it is a great privilege to have you here, sir. Welcome.
Thank you Ritika, and thank you CA for inviting me to this.
Thank you, sir. So how do you feel, sir, today joining us for the interview? And
yeah, it's wonderful actually. So I might not have seen you guys after the class. So I think this is a good way to have more interactions and discussions between faculty and student in the campus. Yeah.
Sure, sir. So you started in civil engineering. So what was the class or the project that made you realize maybe I should look into the sky more than the foundation? What was it, sir?
Yeah, I understand. You are referring to my being more into atmospheric or climate sciences. Yeah. I would say rather civil engineering, when I was doing, there was also this hydrology lectures. Right, that is where I started to getting more fascinated about the hydrology cycle, rainfall and how it affects, and that all comes from your civil engineering background itself. And then as I moved out of my BTech and I was starting my graduation, I realized that, or from the same experience you can guess that I started to like the fundamental sciences more compared to application of civil engineering. I think that somehow is the base where it all moves from. Means it's not. So I was a field engineer for 2 years in Sapurji Palanji. So it's not that I have not seen the foundations, but after doing that, there was always an interest of fundamental sciences, and that's where, and basically from the hydrology classes and environmental classes. Yeah.
So you transitioned into a complex field, like from to atmospheric science. What is the, like when we are learning something, it is not about learning but relearning and unlearning. What was the biggest unlearning in your field you would suggest or say?
Yeah, good question. So I would not put it as unlearning civil engineering, but as unlearning what we do in our BTech curriculum of engineering. So generally, if you look at our curriculum, we have we want to give the students exposure of different modules in a given field of engineering. For example, civil engineering, it's such a plethora of things, starting from BTCM, going even up to environmental engineering. And then when you start your research or get into your postgraduate, so it's a fascinating world. Like you will be given a particular small problem, and then you spend 2 to 3 years understanding what is the problem, how this problem can be attacked, or in a terms the problem solving aptitude starts to build in you. And it being a small area, and if you are excited about that area, at the end you will start to feel that you understood the actual problem, you also understood how you are going to deal with that problem, and also have a solution. So it's knowledge creation. In general engineering, what we do is knowledge application. So you get textbooks and understanding of this is the knowledge already present. You make designs out of it or apply it to real life. And when you say atmospheric science, or in my case more about fundamental science, it was more about knowledge creation, and that's what fascinated me more, I think.
Okay. That is a great perspective to look into how you are looking, because most of the ideas, they germinate from curiosity, and then we are forming a skeleton. It is not like forming a skeleton and then going into things. That is a great thing, sir. So you did your integrated PhD at IIT Kanpur. So what was your biggest aha moment that you had when you realized atmospheric science was your passion?
So, as I mentioned, I was more interested in hydrology. So, and I was, after my BTech, I was in a job, in civil engineering job for 2 years. It's a construction engineering. And then somehow I felt I should try newer dimensions, and I was selected in IIT Kanpur. So I joined there, and during the first few lectures I realized that generally by that time air pollution was not a conventional topic to be taught in engineering, but IIT Kanpur was ahead of time at that point. So we and they had curriculum with air pollution. It attracted me a lot. Obviously water pollution or wastewater pollution is something core of our civil engineering, environmental engineering, but air pollution was fascinating. What was even more fascinating was there was a LIDAR, a ground based LIDAR, which can sense the atmosphere up to 20 kilometer, right, 10 to 15 kilometer. And in a project I initially was working on the output of this LIDAR, and surprisingly we started to see that there is a big layer of pollutants present at 1 kilometer above the surface.
Okay.
And it was not so intuitive to me. We used to think that air pollution is something that you see here. But particles or small particles are present even in the atmosphere, and there is a layer which is flowing like river. All this was very fascinating, or as you term, aha moment. At that point I decided, so I joined for MTech, but once I was like 6 months into this project, I thought this is what is very fascinating for me. And to be very fair, I went to IIT Kanpur to apply for IES exams. Right? After the job, a little bit of phase where I thought I will apply for exams. But during the first year, I saw a lot of research-oriented things happening. And that's why now here we also encourage students to come and do projects. We see a lot of BTech students coming and doing. I think that is important. For me also, it was kind of a short project which evolved interestingly. And yeah, I would definitely, I was very surprised with this. Also, after like 6 more months, I was also into simulating weather. So just means at that point, just imagine a BTech, after BTech, someone would come and tell you there is a set of mathematical equations. If you can solve them numerically, you can simulate the storm happening outside your window. That was very fascinating. I would accept that I was not into too much of computational at that time in my BTech. So that opened up another aha moment, that computational engineering is a very fascinating thing. And simulating a storm which is just happening, it might be off by time, but we can simulate and we can do experiments with it. The physics behind that, those are actually, I would term as my aha moments.
I'm pretty sure that gave a strong foundation for you, sir, because everyone is thinking that when we are seeing each other, that is where pollution is occurring, and 1 kilometer above we are like, oh, this is where exactly the dust particles are present, and that is something great. And as a BTech student, after working for 2 years, seeing tangible things like putting columns and everything, when you are able to solve one mathematical equation and able to predict what is gonna, you felt great at that moment. That is.
Means the scope of these things fascinated me. Means I was still just getting exposed, but seeing that this is such a big world outside which without doing research or without coming into a graduate course, we are missing it, and the possibility of things that can be done, that's very fascinating.
So it is good to expose ourselves to various things, so that we'll get to know about that thing and also about ourselves.
To know nowadays, like after, so this is, I'm talking about 2009-10, right? Now you see the application of robotics, the application of computer vision, all in civil engineering itself. Means we are also now doing some experiments, and I'm seeing now the possibilities are even manifold. Compared to that, I believe the students, if they get exposed, every 3 months they will be getting aha moments for them. And it's very fascinating the way it's moving actually.
You spent 3 years at the Pacific Northwest National Lab. How did your experience with large international research teams change the way you approach a scientific problem?
Even before PNNL, in my PhD time, I spent 1 year in Colorado. So that was a big lab, first experience of my big lab. And 2 things which I learned from my experience there out of international. One is, for example, I just mentioned about a weather model, right? So these weather models are created by more than 100 scientists in a span of 50 years.
Oh.
So you understand the collaborative effort behind that. So it's so much of time taking, as well as without collaboration one person cannot do it, or one organization cannot do it. And atmospheric science is a community which is totally dependent on it, right? If you have noticed, like 2 years back, I think climate scientist got a Nobel Prize for it. So he started this climate modeling research somewhere in 1950s or 60s, right, earlier that time, and many people were doing. When I was introduced around 2010, so it was like 50-60 years of work coming together as a set of Fortran code, right? Someone sitting in a lab here, so opening up those Fortran code was fascinating enough. Once you go to that place where people are actively working on it, you see the courage with which they code it, right? That was, so two things. One was the amount of collaborative or the background effort going into solving such kind of fascinating problem, right? Second is the courage with which the students are approaching. So they know each code or each portion of code they are going. They know everything about it. They are recreating the codes for their experiment. These two things actually gave a lot of perspective. One is we should, as in India, we at that time numerical modeling was very nascent, because computational power was also very nascent, right? But and at the same time, like even to compile this big Fortran codes was a lot of effort. So, and when you go there and you see that people are actually rewriting the codes inside that, compiling and doing numerous experiments, that's what I brought back with me during my PhD time. And I actually did some modification in my codes, which made me confident that this can be done. Then in my postdoc time, it was even bigger project of modeling, and I think there I really see how everyone can put compartment of codes together, right, and merging together, and technical advancement of coupling of processes can actually give very strong accuracy in the simulations. So yeah, it's a bit technical, but to what I am trying to say is these are big codes. After a lot of people come together, not even at the same time. It's a progressive, it's a serial thing. It's not that 2000 people can do it, because technical challenges are there. So to validate this code, you have to do field campaigns of bigger scales. Like for example, you are talking about something at 2 kilometer. You need to do aircraft campaigns to model it. So it's a systematic technical advantage or advancement of both observations as well as modeling it, and then also the courage of so that you can contribute to a smaller part, then there will be other people who will be contributing to that and developing it. So I was part of a project with NASA, and there I learned, so one part was this climate modeling, another was the benefit of satellite observation. So NASA was why they have contributed so much or invested so much in 30 years to build Earth observations to this extent was very clear. A little bit of advancement in observation feedbacks to the advancement in model and process level understanding. So that's the amount of fundamental knowledge that comes with coupling of scientists as well as technologies together, coming together.
So there should be a great balance between the courage you have in yourself and the harmony you're working with all the person who have worked previously and also the people who are working with you now.
Yes.
So that is quite fascinating. It's very much like how termites build their nest. It is so beautiful, but everybody has their own work and then they are concentrated in it and they are going. But at the same time, you have to be in harmony with the other people also working.
And so also I started to realize there is a means this is how mankind have developed actually.
Exactly.
So you at this particular point of time, there is a certain technical thing people are doing across the globe. We don't know what the people or the scientists coming after us can think of. There is immense possibilities, right? So that's what actually was a good example is this numerical or climate modeling. So when somebody was starting, I don't know how great the visionaries were. Obviously they could see they were visionaries, but also doing or having the technical advantage now. For example, AI.
Yes.
So now everyone is talking about the power of AI. There are two things. One, applying them without much depth. Another is again understanding the basics the depth properly and applying, that opens up numerical pathways for all type of problem solving. These are tools actually, right? A model is a tool, an instrument is a tool, right? We still coming back to so there are fundamental questions we try to address. The tools keep on changing with the technology. So more technically advanced tools helps you understand the problem better and
solve it with much efficiency. Yeah, that's true, sir. And one interesting thing was your work highlighted that dust is a bigger threat than the black carbon to Himalaya snow melt. Can you explain the finding quite a bit simply and why we all should care about Himalayan dust also?
Yes. So coming back to my first aha moment.
So 1 kilometer.
Yeah. So those observations actually in my PhD or early master's time, we started to see that North India has a big layer. Big layer means around 2 kilometer thick layer of dust particles in the atmosphere. So these are not present near surface, right? It's like a layer flowing, right? So and advent of satellite data started to show that these are getting originated in the arid regions like Thar, even back up to Saudi Arabia. So wind flows, westerly winds flow. So I would like you to imagine the North Indian map. You have Arabian Sea this type, Saudi Arabia, westerlies are flowing, Thar desert. So the wind is bringing up or emitting dust particles. And as it moves into the North Indian region, this layer starts to move up. It's as simple as you see a chimney, no? Anything, any plume is emitted, it will start to disperse, right? And there is also some complex interactions with the boundary layer, day and night. So in the night time, the temperature decreases, in daytime it increases. So a layer of atmosphere, it's also getting affected, no, by the temperature. So if something is getting emitted and at a place this is happening, then it also raises up, right? It starts to interact. So I will skip the complex part, but this dust layer, where does it go? So if it keeps moving, it is reaching the Himalayan region. So in my postdoc, I came back to this same question. I wanted to know if this is getting deposited on the Himalayan snow. And if it is getting deposited, and there were some initial results from satellite data also. So people there was a field campaign in Nepal where they were saying that a lot of pollution is getting deposited on snow. So what happens is snow is very white in color, or its albedo is very high. So amount of solar energy coming, almost everything is reflected back. Now if I start making it grey or black, it will absorb energy, and then that changes the hydrological cycle. So that was the context. If these particles, we know there is a lot of particles flowing at that height. So if you extrapolate it, they will be going and depositing on the snow. How much they can affect? For this, as I was saying, we coupled models together. A model which can say how much of particles are in atmosphere. Another model which can predict snow. This getting deposited on snow, the energy mass balance, and then melting. So this is how you start to couple climate models, right? There can be uncertainty in properties, but a broad understanding starts to evolve, or the feedbacks. For example, it's deposited, it's darker, it melts and go away. So then a certain period, it is not snow covered anymore. That can affect the temperature, the climate back, right?
Yes, exactly.
So those are the feedbacks. So this is what is the basic of this. So before this coupling of dust, we used to think that pollution from fossil fuel like black carbon, they are highly absorbing or warming, and they get deposited and is affecting the snow. Our results show that this layer of dust is equivalent, or at least equivalent, if not more. And at higher elevation, this is higher because it is at higher level, right? So that was the context of it, and it has a uncanny implication. One is understanding that we don't know much about it. You have to do field campaigns because we have been modeling and interpreting. If you add another process, things are changing. So in situ observations are needed, which we don't have. Second, this is a natural particle emitted by wind and dust, compared to a black carbon which is emitted by anthropogenic activities. So how to reduce this is also a mitigation challenge, right? And if we miss this, the impact we are missing. So it opens up a lot of questions, that not only black carbon, we have to think about other particles also which can be equivalently affected.
So it is like a web that has been connected. The problem where we are starting could be Himalaya snow melting, and we can trace it back, or we can know that there is a lot of dust coming from the western winds that is carrying, and then we can address it the same way. And as you told in the previous thing also, so as research for this, there could be other parameters also affecting the Himalayan.
So it will be affecting our regional climate back.
Okay.
Because everything is thermodynamics. If the temperature of there is famous theories that the temperature over Tibet drives our monsoon.
Okay.
So I'm trying to say how thermal changes is affecting the dynamics. So there is always a thermodynamical link. So the better we can understand the processes, there will be thermodynamical feedbacks to the regional climate system.
And based on this settling, how when Himalaya snow melts, what about that feedback because of the melting? What happens?
Correct. I'm saying if you couple it and run it for a longer period, there will be feedbacks which we don't imagine, and it will start to show up.
That might be quite surprising also.
And that's the benefit of climate modeling, because you cannot measure those things.
Yes.
It can only be modeled, and hence the importance of or the fascination of climate
simulation
modeling.
and other things. Great, so that is so. And your research showed that pollution can actually cause a cooling effect during the Indian monsoon. Now we are in the monsoon season too. Yes. How do you explain this paradox to someone who only hears about global warming?
Yes. Yeah, this is also means you have to envision this, and again the benefit of climate modeling into this. A cloud is formed when a parcel rises from surface.
Yes.
As it rises, the temperature decreases. The moisture inside that starts to condense, right?
Yes, sir.
On what?
Air, atmosphere.
So always, so we have in school, there used to be examples, no? There is a cold glass of water, and then there is a droplet formed all around, right? So it needs some surface.
Exactly, okay, got it.
So these particles, the pollutants, actually act as that surface.
Oh.
So when the parcel rises, temperature decreases, moisture is ready to condense, it needs a surface. These particles are that surface.
Okay.
So in a place, or theoretically if we have a closed air mass, the number of surface will also affect the number of cloud droplets to be formed. That's the basic of one impact of pollution on cloud.
Okay.
Right? It can affect the number of cloud droplet as well as the size of cloud droplet.
Okay.
And what happens because of that? So for example, you have a bigger droplet versus a smaller droplet in a volume of air, right? So this one is more mass, and it will act to move down.
Okay.
This is less mass, more buoyant. It can go even still higher.
Yes.
And you remember, clouds are formed under a updraft. So when the air rises up, then only clouds are formed, right? So naturally it is buoyant. What happens is, when condensation happens, it comes down. That's exactly rainfall. Those cloud, it's condensed. Now this is coming down.
Okay.
As it coming down, more moisture is getting condensed. The particle which is big enough to reach surface is rainfall. Another I would say a very interesting fact. You see clouds in sky, right?
Yes, sir.
So it's always raining.
Okay.
The drops are not reaching surface.
Okay.
They are getting evaporated mid-atmosphere because they are not big enough. If the cloud has enough moisture, it will form bigger droplets and it will reach. For example, in the campus, you will be moving. Suddenly there will be some pores on you without anything. Right? Why is that?
They are large enough to come down.
They were falling and they could reach it.
They could reach without evaporating.
In many cases, they could evaporate.
Okay.
So means a easy way to look at it. It is much more complex than that. But so coming back to the fact that if you have lot of pollution in a rising parcel, it can change the microphysics of cloud. How big the cloud droplet is, then how big the rain droplet will be. So if the parcel will move up or down, these things it starts to change. So we did satellite analysis as well as high resolution modeling to show that these we have a lot of particles. There has been aircraft measurements from Indian government where they calculate what is the amount of particles present in a control volume of air in India during monsoon period. It is like 2000 to 3000 particles per cc. If you imagine, it's a lot. Per cc of a parcel, there is 3000 particles, right? And assuming that the moisture is same compared to a pristine condition, for example in Andaman Nicobar, Andaman Nicobar, it will be around 500-600 particle per cc.
Okay.
So if you compare these two scenarios, then in the Indian landmass, the cloud droplets are much smaller. Hence, the cloud parcel, instead of theoretically coming down because of weight, relatively it will be higher,
higher
relative to that. So higher it goes, there is another factor which comes into picture, right? Freezing temperature.
Okay.
Right. For example, what is the temperature here at surface?
20.
Something 25-30
25,
in
yeah.
monsoon. So what will be it at 1 kilometer?
Not sure.
So we have strict lapse rates, right? We know every kilometer there will be a 9 degree or 6 degree decrease in temperature. So within 3 or 4 kilometers, you will reach the point where it goes negative.
Okay, so freezing will be there.
That is known as freezing. Now imagine this cloud parcel crosses that, right? So now instead of falling as rain,
It will freeze.
they will freeze as ice drop. And now the density increases, it will start to fall, and it is intense. So ice falling, evaporating and getting down as big raindrops, right? So what happened, if you are catching the explanation, a polluted case, clouds are getting bigger.
Yes.
Because the water mass is going up. When it rains intensely, because now what is falling is bigger ice pieces. So the velocity of falling is high. By the time it reaches, it melts from ice to water and rainfall happens.
Okay.
Right? Third, as the cloud is bigger, so if you have seen, if you are in a flight, you look out of the sky, you have seen clouds.
Yes.
How does it look?
Like cotton, something like that.
That is one. You can also see some towers coming out.
Yes, yes.
You can see
that is there. Yeah.
means whenever there is a tower, you will see a mushroom kind of thing protruding.
Yes, yes.
So whenever we say the clouds are bigger, there will be a mushroom kind of thing protruding.
Okay.
That is known as anvil.
Oh,
Right?
anvil.
If I am saying the clouds will be taller, bigger, more rainfall, it also shows that the anvil will be bigger.
Okay.
This we have checked from satellite data as well as modeling it.
Okay.
Now your question I can answer. If the protruding anvils are bigger, this will reduce solar radiation from reaching surface.
So they won't evaporate. They'll.
And no, just for example, if you have clouds,
Okay.
solar radiation will not, or it will capture some of the solar radiation coming in and reflect it back.
Okay.
So whatever we are reaching at surface will reduce compared to if there is no
thick-
cloud.
Yes.
So bigger the anvil, more is the reduction of solar radiation
Yes, sir.
and hence a cooling effect.
Okay.
So contrary to the fact, if aerosols are increasing, they in monsoon specifically, they are also contributing to bigger cloud anvils
Anvils.
and towers in our case in the monsoon, where moisture is not limited. If you add more particles, moisture is condensing into smaller cloud droplets and it's going up, freezing and becoming bigger, right? As a result, less solar radiation is reaching surface. Hence, there is a cooling effect,
Cooling effect, okay.
against the general notion of warming effect. And there is contrary effects also, which we are now starting to see from using models.
Okay.
So what I just explained is one mechanism or contribution of air pollution. That is what we studied. But warming itself has a role to play with cloud dynamics.
Okay.
That is even more complex. We have not even measured it and we are trying to model it. But yes, again, I accept non-intuitive results. But this is why we need to have more studies in this direction. It's definitely complex. And even 1 or 2 studies, if we do this study again, right, after 10 years, the background environment might have changed so much that these results might change. It's still hard to generalize these things. But yeah, that's why it's more interesting.
Yeah.
Yes.
The complexity makes it more
Complexity
interesting.
makes
But thank you so much, sir, because I was able to understand, though I'm not in an environmental engineering background, I was able to understand, like, so the dust we are and the pollutants we are is literally forming like a shed over us where the radiation is being protected and then this part is cooling. Most important thing about learning is that are you able to explain it to another person in the simplest manner possible? And I think you are very good at doing it. Thank you, sir. So next is, you have studied about urban heat island effect, the one that is predominantly. If you could mandate one change to city planning in India right now to immediately lower temperature and pollution. Now I can understand it's not that easy, it's quite complex. But on a general note, what would it be, sir?
Yeah, means I can have a simple answer, but towards the end we will again see the feasibility. Simple answer we all know, reduce fossil fuel consumption, right? And that is the core of sustainability now.
Yes.
Even what you say is part of urban resilience towards sustainability. So if you reduce fossil fuel usage, you reduce the gas emissions, which is the greenhouse gases at some point. You also reduce the particle emissions, anthropogenic particle emissions, in mainly the black carbon, which is very absorbing in nature. So that also contributes a lot to the warming or destabilization of regional climate. Right. So I understand urban heat island is more about the center of urban being there, but till now I still feel that the change in energy usage, right, can have means some minimizing effect on it. And secondly, which is even more easier, is having trees. Right. So some green coverage. So now government is coming up with policies. For example, recently Tamil Nadu State Planning Commission announced a policy 330-300 meters. So certain amount of trees should be present within near which can be seen from your window. Within 30 meters, within 300 meters, there should be park. So this, what we are trying to say is, a urban region having a green fraction is much better if we don't have a green fraction. Green fraction is the sink for both the carbon dioxide as well as heat out of it. And at the same time, if you talk about pollution, it's the energy what we are using. If we start shifting into our renewable energy, which is we are in very good inertia has been created. So for example, what we should be doing is quantifying that. For example, California state, they start to quantify, solar energy can run this city for 5 hours a day. Wind energy can run this city for 3 hours a day. So when they say that this city can run 24 hours a day by renewable, then the entire energy conversion has happened. Right. So I really like that kind of metric when you hear about it. I think it has to be initiated by big city specific means stakeholders. How much solar energy can actually contribute for running Chennai for how much hours, and then start to increase it. What policy level changes are needed to increase it. So yeah, these are the thoughts I believe.
Exactly. The qualitative aspects are, we have a lot of ideas in qualitative aspects. Now it is quite some time that we also shift our attention to quantitative aspects, because that is what will give us how much more of a leap we have to go through to reach our goal and other things.
And I feel that is where our BTechs can be very efficient. Means now obviously I also feel that the engineering disciplines are becoming interdisciplinary. Right. So, and also the way technology is merging, you have knowledge at your fingertips now, right? So every day morning, if I open YouTube, there is an ad. It says like, go away for 30 days, come back with AI powered this, right? So I think in 30 days, if you are getting a confidence that you can have a skill, it is a beautiful period to be in. And in same way in robotics, electronics, there is a lot of scope where even civil engineering students understanding a problem, then again bringing the advanced tools which are available now to solve it, right? For example, this UHI you mentioned, we still don't have too much of data, right? Which can be addressed by small IoT projects. Entire Chennai, can you build a grid of temperature RH observations, right? And this can be very exciting as well as learning, and at the end rewarding also. Most of the Europe cities are benefiting from citizen science in addressing urban heat changes, because you cannot go every lane. It has to be the citizens present who have to help, right? And once you have more data, you can have better policies in this direction.
That is true. Because every citizen, not just people who are working towards research, every citizen who is also of a greater impact. That is true.
And in India, pollution is also at that level. It's not only heat. So
both are.
So our cities need more contribution of citizen science, and that can be starting with graduates. BTech students are doing very good.
Exactly, sir. Because one person's perspective and knowledge can change a million people too. That is true.
And I'm seeing the people are doing a lot. There is a lot of this hackathon startups for sustainability. I see, I've been judging a few of them. I'm really impressed the way we are moving. It's great to see. I would like our students to participate more.
Yes, it is also a beautiful time to be in and to develop a lot of technology. Yes, sir. So, What's the most rewarding part of being an associate professor in environmental engineering at IIT Madras right now? And what is the biggest challenge you see for new students who are entering the field?
Yeah, obviously the most rewarding part is students. So it's also a great privilege to be in IIT Madras. The environment is good here. So everyone is like trying to do something. Everyone is busy, I would say, and it's a good thing, right? And having meeting so many, and we have a good culture of interdisciplinary research. So meeting people, most of my research I do is interdisciplinary because we don't have a specific kind of thing. So, but it is also rewarding when you discuss different aspects interdisciplinary. It is very rewarding. So just now I mentioned, so we have developed some equipments which we would not be able to develop if only civil engineering is there.
Yes.
We participate with electronics, we participate with engineering design, and we are making them. School of Sustainability. They are enabling now students to have living lab projects, right? And obviously that will end up with new interdisciplinary facts coming up. So one thing is definitely the ecosystem here. Startup ecosystem here, and third is students. Your students are good. So if you have some hypothesis, both fundamental science or something you want to try hands-on, there are students who are interested to work on it. As a scientist, like I have been scientist in national labs, I think that part we definitely miss, and I definitely feel that more interaction of BTech students can make it more enriching.
Yeah, that is true. Because when we have divided into subdivisions so that we can concentrate on one thing more. But when we are addressing a real life problem or situation, it is something like a chain or web of various departments connected together, and it is highly rewarding to be interdisciplinary because everything is interdisciplinary.
Yes.
Exactly. And what is the single biggest open question in aerosol climate science that you hope to answer in the next 5 years?
So actually there are many. So as means I explained to you two different scenarios. Both are complex enough, right? So I am working in both directions. I would not be able to claim something I can solve in 5 years, but I can share what I am thinking I will do in next 5 years. So I am working on both understanding how these particles reach Himalaya snow. So we have started to go for field campaigns there. And we have selected a glaciated catchment where there is a glacier, there is snow component, there is water component, and this we are collaborating nationally with four or five national institutes. There are colleagues who come with their expertise, their team. So you imagine going to a glaciated catchment off grid for 10 to 15 days. It's not possible for a single person or 2-3 people with 2-3 students, right? So it only happens if we come together 20 people trying to go there, stay there and do various observations. We have also built international collaboration into it. Now we have some funding also where we have actually instrumented the catchment. We are measuring how glacier is changing, we are measuring how snow packs are changing, we are measuring the flow changing, aerosols reaching there. So all these things we have started measuring from last year. So we will be measuring for 3-4 more years. Use that to build better models to understand how particles are affecting glacier melt and the overall cryoscope, right? Similarly, in terms of clouds, right? I am still focused on understanding particles affecting cloud. I have worked on monsoon clouds. Now, just to bring another complexity, clouds is not binary. It's not cloud, no cloud. There are 9 types of clouds.
Columbus and other thing.
And for example, fog, right? It's a big social economical problem in North India. It's very different cloud, right? Trying to so what I explained, everything dependent on a parcel rising up. In fog, it doesn't rise up. Actually. Then what happens? So those kind of questions we are trying to observe, answer. Overall, in next 5 years, I would like to better understand these particles, the chemistry of it, how it is affecting cloud droplet formation, and hence the lifetime of different clouds, the structure of different clouds. I mentioned monsoon clouds are getting bigger, it's having a climate effect. With a PhD student, we are working on fog clouds. We are seeing some similar nature, but very many things are different, trying to explain what is happening because the dynamics is different. Similarly, here in Chennai, like students, I would really encourage, if you look up at sky, start looking every week sometime consciously, you will see very small beautiful clouds moving around.
Yeah.
Right? So we are blessed because it's a coastal system and we have lot of rolling clouds formation, and these clouds are very hard to measure.
Yeah.
Right?
Yes.
So we are doing experiments here in our satellite campus. We are measuring the pollution along with those clouds and also building models, model based understanding. If it is for example, we are also measuring updrafts.
Okay.
Right? If this parcel is forming a small cloud with this much amount of particles, are our models giving the good idea of what is happening? If so, better constraining our models. If that is not correct, then we cannot say how our aerosol climate interaction will be. Right? So just to cut short, both scenarios I am trying to build the fundamentals even better and bring it back to the models. Hence we can say how aerosol climate interaction is happening. Right? So yeah, I think that is where I am going.
I mean, measuring the glaciers and the spot you are telling, that is a great milestone, sir, because now that we can get the realistic data of what exactly happening and validate our model and then bring our model changes, that is really a great of a milestone. And I don't think I'll be looking at the sky the same way I look at after this conversation, never. Because if somebody is going to ask, is it raining? Maybe it is not teaching.
So I gave you a aha moment.
I had my aha moment today. Like, yeah, maybe it is raining. It's just that it is not reaching right now. And okay, a final question. And why did you feel more drawn to from research to teaching, from being a student to a lecturer? Or both of them are learning, but why did you transition from one to another?
Yeah, so I will be a little retrospective in this question. So yeah, means when we start doing research, for example, you are a PhD student. You take some topic. Now I know your topic is digital twin in a building, right? After 5 years, mostly this topic will be solved by you, by many other people. So first understanding of evolution of research was that you are learning how to do research. You are not learning research on digital twin of building. Right? So that was one. Means I am just sharing retrospectively what is the evolution of this question. Then after 5 more years, you might have taken up as a postdoc or as a young faculty 2 different projects which are different from this one, but something is related. The backgrounds are related. By that time, you will be very clearly understanding that you have to learn new things. You have learned what is the approach of research. Now you have to learn new things in limited time and deliver. In that process, if you are a faculty, then you have to also train students like you are getting trained, right? This is the evolution of research. So when you say teaching, teaching is also part of it. Another aspect of it is, and I will quote some of my colleagues also here. So when I joined, they told, if you want to learn something fast, teach it.
Exactly.
And at that point, now I am very certain why it is true. You will be under pressure to learn something fast, understand and teach. Then you have students like you have in IIT. You have to answer questions. They are beautiful minds, right? So one is, when you are doing research, you are evolving into new topics. You are anyway learning and teaching to students. At the same time, if you are teaching core courses, then also it's the expression, right, which helps you to do your research better. Because also now I could express because I could teach better.
That is true.
These are some thoughts.
Yeah, so that the journey you told about how you are first learning how to do research, and then comes your topic, and then comes various topic. That is something, a keynote or a cornerstone that we'd like to know. And it was really great. Thank you so much, sir, for being with us and then sharing everything. Because I would like to thank you again, because environmental engineering is not just one thing. It's a complex of things that comes into picture, and explaining things to us, it was really nice, and then we were able to understand not only about the topic, not only about the environment, but also about how learning as a process unveils, and then how the transition happens, not only in research and other things. It was really of a great pleasure.
I would like to connect that teaching helps you know this.
Exactly.
Only when you teach and you see that somebody can understand what you are saying, then your learning and evolution happens. So teaching is very important if you want to grow in your research.
So true, sir, because we do our TA duties right here. So when we are relearning the subject, the questions they are asking. Like when you are put into a new concept, we would have assumed a lot of things, but when they are asking questions, you will like, is this an assumption that I never questioned, or is it something I should work on, and things like that. Thank you so much, sir. It was a great insight, and thank you so much for spending your time, sir.
Thank you.
Thank you.